So here's another example of a galvanic cell. So we have on our positive side, which again, that is our positive is where the electrons are going to. So that's the reduction side. So this is the cathode. We have silver there, and on the anode, the oxidation side with the cadmium. So our cathode reaction, this is the reduction. So we have two silver ions reacting with electrons to form silver metal. And on the anode side, we have cadmium metal giving up two electrons to form cadmium ions. And so our net reaction is that we have cadmium solid plus two silver ions reacting to form cadmium ions plus two silver metal atoms. Okay, so I want you to pause. Look at this. What voltage would you expect for this solution? Would it be positive, negative? What information would you need to know? If so, so if we attached a potentiometer to this cell, what would it read? Okay, so this is a little bit of a trick question. The voltage for this particular cell, as shown here, is 0 volts. This won't measure any potential difference. Now, why is that? Well, the reason for that is that the electrons, we'd like them to go, of course, we'd like the electrons to go from the cadmium through our voltmeter here down to the silver, but they don't have to, because there's nothing stopping them from just going through the solution here. So the electrons can just be exchanged right here directly in the solution. And there's nothing to stop them from just, right? So the silver ions can just go right over here to where the cadmium metal is and react directly there. So there's nothing here to prevent the electrons from doing that, and the electrons won't go through the circuit that we've set for them. So we'll get a voltage of 0 volts for this particular cell. So what we need here is some way to keep these separate. These two half reactions need to happen in different places, and the electrons can only have one way to go, which is where we want them to go, which is through the electrical circuit. So the way we do this is we need what's called a salt bridge. And so this is that same galvanic cell, but now adding in a salt bridge. So the salt bridge here is this is a piece, it's a porous glass tube that's filled with some inert salt. In this case, it's potassium nitrate. And the purpose of this is to maintain electron neutrality. If our electrons want to go right from our from our negative to positive potential, right? If they go from the cathode to the anode, no, from the anode to the cathode. Got to say it the right way. From the anode to the cathode, you'll build up a charge differential. And so, right, as the electrons leave, this side will become positive, this side will become negative, and eventually that will resist the flow of electrons pretty quickly, actually. So to balance that out, we have to have negative ions from the salt bridge going into the solution and positive ions from the salt bridge going into the other solution to keep the charge neutrality so that the electrons can keep going through the circuit. And so that's the purpose of the salt bridge. It allows, it prevents the silver ions from going directly over to the cadmium like we had in the previous picture, but still allows us to maintain electron neutrality. So we can still have this reaction, but now we'll actually measure a voltage on this. Now, we don't necessarily want to write out a picture showing this every single time, and so we have a shorthand that's used for denoting galvanic cells called line notation. And the idea here is that we have one line represents a phase boundary. So going from, say, solid to aqueous or to a gas or something like that. Most commonly, it'll be aqueous and solid phases. And then we can draw two lines like this, two vertical lines, represents a salt bridge. So a way of connecting our parts of our galvanic cell without them electrically connected to each other, where electrons can flow. So if we take this example here, the way we would write this, we put the actual electrodes on the ends, so the pieces of metal that connect. So electrodes on either end. And by convention, we put the negative side, the anode, on the left, and the positive side, the cathode, on the right. So we would have cadmium solid, that's our electrode that's on the left-hand side. And then we have a phase boundary. Then we have our cadmium nitrate in the aqueous phase. That's the other part of our cell, the other half of this reaction. Then we have a salt bridge, and we write our silver nitrate in the aqueous phase. And then a single line, because we have a phase boundary, and then our silver electrode goes on the other end. All right, and so that's a simple way to write out a galvanic cell. And so you'll see this sort of notation, we'll keep using it in this class, and this is very commonly used in throughout electrochemistry.